In all these examples, we are supposed to determine the asymptotic behavior of solutions without solving the differential equation, right? So the main source of information is the direction field. Now, the first equation is y prime equals 3 minus y, and if you look at the direction field, you will notice that all these arrows corresponding to the line y equals 3, they all point exactly to the right. Right? So it means that y equals 3 is an equilibrium solution. So y equals 3 is an equilibrium solution, which, by the way, we can just find from the differential equation. So we equate the right hand side to 0 and solve for y, and we find that y equals 3. But at the same time, by looking at the direction field, we see that all the arrows, they kind of they are arranged in a way so that all other solutions, they are going to approach y equals 3 when t goes to infinity, right? So it means that here the asymptotic behavior is that the limit of y as t goes to infinity, limit of y of t, is 3 regardless of the initial value of y. This is what we see from the direction field. This is kind of how the flow of arrows, what it tells us. Okay, next. So now the ODE is y prime equals ln of y squared plus 4 over 8. And then if you look at the direction field, so notice that there are two equilibrium solutions here. Well, they seem to be y equals 2 and y equals negative 2. Well, but just let us solve it to make sure. I mean, solve for equilibrium solutions to make sure. We're not going to solve the differential equation, but we will find equilibrium solutions. So to find equilibrium solutions, we write our right-hand side, which is ln of y squared plus 4 over 8, and equate it to 0. So ln of something is 0 means that the argument of ln y squared plus 4 over 8 is 1. Well, so y squared plus 4 is 8. So y squared equals 4 and y equals plus or minus 2. And so these are the two equilibrium solutions. But furthermore, so notice that if the initial value of y is above 2, then as t goes to infinity, it just goes to, the solution goes to the positive infinity. But if the initial value of y is less than 2, then all those solutions, they approach negative 2. And this is the asymptotic behavior. So the asymptotic behavior here is that if the initial value of y is bigger than 2, then the limit of y is going to be infinity. And if the initial value of y is less than 2, then y is going to approach negative 2 as t goes to infinity. That's the asymptotic behavior. So in our next example, y prime equals t minus y, we do not have equilibrium solutions anymore, but we do have something like this. So notice that here there is kind of all these arrows. They are arranged along a straight line. So they are all parallel to this straight line. And they kind of follow the straight line. So it means that this straight line is a solution of the differential equation. And the straight line is, well, actually y equals t minus 1. This is a solution. It is not an equilibrium solution, but you can easily verify that it is indeed a solution. So this is some solution. It's not equilibrium solution. But at the same time, from the vector field, we see that other solutions, they approach this solution. So it means that here, the asymptotic behavior of solutions is that, so they do not approach a particular limit, but it means that, well, the line y equals t minus 1 is an asymptote to all solutions. So is, well, asymptote to all solutions. Next question. Determine asymptotic behavior of solutions of these differential equations. Now, what we definitely see from the picture is that regardless of the initial value, well, at least for most initial values, if t goes to infinity, then y goes to tends to plus or minus infinity. So sometimes plus infinity, sometimes minus infinity. But at the same time, that there is a certain pattern. So like, I don't know, if we're here, then it goes to plus infinity. If we're here, it goes to minus infinity. But that there is kind of a parabolic pattern in between them that you see is kind of this parabola is a solution, and all other solutions they kind of as t goes to infinity, they drift away from this parabola. So there is a certain parabola is a solution, certain quadratic function. So which I don't know. I mean, I guess we can try to guess that quadratic function, but it's probably not obvious immediately what that quadratic function is. Quadratic function. So there is a solution that is a quadratic function. Well, and then if t goes to if t tends to infinity, then other solutions they kind of drift away from this quadratic function. But at the same time, if t approaches negative infinity, then all solutions they kind of approach this quadratic function, right? Well, the word asymptote usually means that our solutions approach a straight line, but here we have a kind of a similar effect. So we have a quadratic function, and if t tends to negative infinity rather than to positive infinity, then all solutions approach this quadratic function. Okay, so here we have the differential equation y prime equals negative y plus cosine t minus sine 2t. And what we see here is that it's hard to tell exactly, but there seem to be some kind of oscillation here in the middle, and all kind of other solutions, they approach this oscillating solution, right? But that oscillating solution is really, we can't really tell what it is from the plot. Well, which means that's the answer. Unless, I mean, of course, now after lecture 2, you know how to solve this explicitly. But even without solving it explicitly, what we see here is that asymptotic behavior is that solutions approach some oscillating solution. Some oscillating solution. How to find this oscillating solution? I guess, I mean, either you solve the differential equation, or you probably can guess like that this should be some combination of cosine t, sine t, cosine 2t, and sine 2t, because they're here. Okay, and finally, one more example. Determine asymptotic behavior of solutions of the ODE y prime equals y minus 2 times y plus 3 and times cosine t. So notice that here we have y equals 2 is an equilibrium solution. Y equals 3 is an equilibrium solution. Sorry, y is negative 3 is an equilibrium solution. But do other solutions approach either of these two? Well, actually, no, because all other solutions seem to oscillate. So if you have a solution here, then this kind of goes down, then probably goes up again, then probably goes down again, then goes up again, goes down again, and so on. Same here. So if you have a solution that approaches y equals 2, and then it goes up, then it probably goes down, goes up, goes down. Well, it's not so obvious too. But in any case, you see what we see here is that there are two equilibrium solutions, y equals 2 and y equals -3. Then other solutions, they, as t goes to infinity, all other solutions, they oscillate, so they do not approach either of these two. So solutions with the initial value between 2 and -3, they oscillate between 2 and -3. Solutions with the initial value bigger than 2, they oscillate so that they kind of the minimum of oscillation is still above 2, and solutions